Picture this: a universe cloaked in endless darkness, a void so vast and silent it defies comprehension. Then, in an instant that rewrote reality itself, the first flicker of light pierced through the emptiness. What sparked that cosmic dawn? What mysterious forces conspired to ignite the very first elements that would one day become the building blocks of stars, planets, and even us? The answer lies in a story so profound, it stretches back to the birth of time itself. Today, we're diving into one of the greatest mysteries of existence, the universe's first light elements. These primordial ingredients didn't just shape the cosmos, they set the stage for everything that followed. Think about the hydrogen in your body, the helium in a child's balloon. These simple atoms are cosmic relics, forged in the furnace of creation over 13 billion years ago. But how did they come to be? Scientists have spent decades unraveling this puzzle, and what they've discovered is nothing short of astonishing. Some theories suggest violent collisions between particles in a searing hot newborn universe, while others point to exotic processes we're only beginning to understand. One thing's for certain: the origins of these elements are far stranger, far more spectacular than anyone could have imagined. And that's exactly what we're exploring today. 30 groundbreaking theories about the universe's first light. From the wildest edges of astrophysics to the most meticulous lab experiments, we'll journey through ideas that challenge everything we thought we knew. Could dark matter have played a role? Did bizarre quantum fluctuations kickstart the whole process? Or is there something even more unexpected waiting to be uncovered? Strap in, because we're about to travel back to the very beginning, to a time when the universe was just taking its first breath, and the first light was about to change everything. At the very beginning, mere fractions of a second after the Big Bang, the universe was unimaginably hot and dense, a swirling chaos of energy where atoms couldn't even exist. But within minutes, something extraordinary happened. As the cosmos expanded and cooled, the first light elements burst into being in a process so precise, it's almost like the universe followed a cosmic recipe. Scientists call this Big Bang Nucleosynthesis, and it's the foundation of our understanding of how hydrogen, helium, and tiny traces of lithium came to be. The key to this theory lies in the conditions of the early universe. Picture a pressure cooker at a temperature of around 1 billion degrees, so hot that protons and neutrons, the building blocks of atomic nuclei, could finally stick together instead of being torn apart by the violent energy around them. In those first 3 minutes, the universe cooled just enough for nuclear reactions to occur, fusing these particles into the simplest elements. Hydrogen, the lightest and most abundant, formed when single protons snagged electrons. Helium came from protons and neutrons pairing up, while lithium emerged in even smaller amounts. But here's the fascinating part: the ratios of these elements match almost perfectly with what astronomers observe today. This discovery didn't come out of nowhere. In 1948, physicists Ralph Alpher, Hans-Bethe, and George Gamow published a groundbreaking paper that laid the mathematical foundation for this theory. They calculated down to the tiniest fraction how much of each element should have formed under those extreme conditions. Decades later, telescopes and satellite data confirmed their predictions with astonishing accuracy. It's one of science's greatest triumphs, a theory so solid, it explains why the universe is made of the stuff we see all around us. Yet even this well-tested idea leaves mysteries. Why was there just a trace of lithium, far less than the calculations predicted? Some say invisible particles, like hypothetical dark matter, might have interfered. Others wonder if undiscovered physics played a role. But one thing's certain: the story of these first elements is far from over. Every answer only leads to deeper questions, pulling us further into the enigma of the cosmos. And this is just the first thread in a tapestry of theories waiting to be unraveled. While Big Bang Nucleosynthesis explains the birth of hydrogen and helium with remarkable precision, there's a twist in the cosmic tale. Something even more fundamental might have shaped their distribution. Enter cosmic inflation, a theory that rewrites our understanding of the universe's earliest moments. Imagine space itself stretching faster than the speed of light in the first sliver of a second after the Big Bang. A sudden growth spurt so violent it could have scattered the seeds of all future matter. This radical idea comes from physicist Alan Guth, who proposed in 1980 that inflation wasn't just a side effect of the universe's birth, it was the engine that set everything in motion. Here's where it gets fascinating. While nucleosynthesis cooked up the first elements minutes after inflation ended, inflation's exponential expansion might have determined where those elements ended up. Think of it like blowing up a balloon with tiny ink dots. The dots were originally close together, but as the balloon inflates, they spread apart in a pattern dictated by how fast the stretching happened. Recent data from the Planck satellite adds fuel to this fire. When mapping the cosmic microwave background, the afterglow of the Big Bang, scientists noticed faint temperature fluctuations that don't quite match predictions. Some regions of the early universe appear slightly hotter or cooler than inflation models anticipated, hinting that the primordial expansion wasn't perfectly even. Could these wrinkles have influenced how hydrogen and helium clustered, setting the stage for galaxies to form billions of years later? The debate between inflation and classic nucleosynthesis isn't about which one is right, they're pieces of the same puzzle. Nucleosynthesis tells us how elements formed, while inflation explains why they're arranged the way we see them. But here's the kicker. If inflation's quirks left fingerprints on the distribution of matter, we might need to rethink just how uniform the early universe really was. Some theorists even speculate that exotic particles or energy fields during inflation could have altered the ratios of those first elements, leaving traces we haven't fully decoded yet. What makes this theory so compelling is its audacity. It suggests that the universe didn't just expand, it exploded into being with such ferocity that its echoes shaped everything from the largest galaxy clusters to the atoms in your fingertips. Yet for all its explanatory power, inflation raises new mysteries. Why did it start? What stopped it? And most tantalizing of all, could there be regions of space where inflation never ended, birthing other universes beyond our own? The answers might lie in the very elements we're made of, hiding clues written in the aftermath of that first unimaginable expansion. Now imagine a universe so young that black holes, those cosmic vacuum cleaners, weren't just rare monsters lurking in galactic centers, but tiny, fleeting specks popping in and out of existence like quantum fireflies. This is where Stephen Hawking's mind-bending theory takes center stage. What if these primordial black holes, some no heavier than a mountain yet denser than a star, weren't just cosmic oddities, but the unseen alchemists behind the universe's first light elements? Hawking proposed something radical in 1974. Black holes aren't eternal. Thanks to quantum mechanics, they slowly leak energy, a phenomenon now called Hawking radiation. For supermassive black holes, this process takes longer than the current age of the universe. But for microscopic ones, potentially formed in the chaos of the Big Bang, evaporation would have been explosive and instantaneous by cosmic standards. Here's where it gets wild. As these tiny black holes evaporated, they wouldn't just vanish, they'd unleash a burst of particles and radiation so intense, it could have catalyzed nuclear reactions in the surrounding plasma. Picture a minuscule bomb detonating in the primordial soup, its shockwaves forcing protons and neutrons to fuse into hydrogen, helium, and lithium. The math is astonishingly elegant. Hawking calculated that a black hole with the mass of a small asteroid would evaporate in about a second, releasing temperatures exceeding 1 billion degrees hot enough to rival the conditions of Big Bang nucleosynthesis. Some theorists argue this could explain slight discrepancies in the observed abundance of lithium. or even hint at pockets of the early universe where element formation happened faster and more violently than standard models predict. But there's a catch. No one's ever detected these primordial black holes, and their existence remains hypothetical. Yet the idea refuses to fade. Recent work suggests they might have left subtle fingerprints, perhaps imprinted in the cosmic microwave background, or even in gravitational waves we're just learning to measure. If they're out there, lurking in the darkness between galaxies, they'd rewrite not just the story of the first elements, but our entire understanding of how the universe bootstrapped itself into existence. What makes Hawking's hypothesis so thrilling is its audacity. It turns black holes, typically seen as destructive forces, into potential creators, quantum forges that might have tempered the earliest building blocks of matter. And if we ever find evidence of them, it would mean the cosmos had a shadow workforce, invisible architects sculpting the elements long before the first stars flickered to life. For now, it remains a tantalizing what if, a reminder that the universe's infancy might have been stranger than we dare to dream. Long before protons and neutrons even existed, the universe was a seething ocean of something far stranger. Quark-gluon plasma, a state of matter so extreme it defies everything we know about physics. Picture a cosmic soup 10 trillion degrees hotter than the sun's core, where the building blocks of atoms couldn't hold together. Quarks and gluons, the fundamental particles that normally bind to form protons and neutrons, danced freely in this primordial fury. But as the universe expanded and cooled, this plasma underwent a phase transition as dramatic as water freezing into ice, and hidden in that shift might lie clues to one of the greatest mysteries of the early elements, why there's far more matter than antimatter in the cosmos. This transition didn't just create protons and neutrons, it could have sculpted their very ratios. During those first microseconds, slight imbalances in the plasma's behavior might have tipped the scales, producing slightly more protons than neutrons. That tiny asymmetry would ripple across billions of years, shaping how much hydrogen and helium formed during nucleosynthesis. Here's where it gets mind-bending. If the transition happened unevenly, pockets of the early universe could have ended up with different ratios of these particles, explaining why some regions today show unexpected variations in element abundances. Scientists at CERN have recreated these conditions using the Large Hadron Collider, smashing heavy ions together at near light speed to briefly resurrect quark-gluon plasma. The results are startling. These experiments reveal how the plasma behaves like a perfect liquid, flowing with near-zero friction, and hint at how quantum fluctuations during its cooling might have influenced the birth of matter itself. One tantalizing possibility: exotic particles predicted by theories like supersymmetry could have interacted with the plasma, leaving ghostly fingerprints in the element ratios we see today. But the implications go even deeper. If this phase transition generated gravitational waves, ripples in spacetime itself, future detectors might catch echoes from that primordial shift. It's a cosmic detective story where the clues are written in the oldest elements, waiting to be decoded. And if we uncover them, we might finally understand why the universe favored matter over antimatter, turning a seething quantum soup into the building blocks of galaxies, stars, and life itself. Dark matter, the universe's most elusive substance, might hold the key to one of cosmology's stubborn mysteries. Take lithium, that lightweight element whose abundance in the early universe doesn't quite match our predictions. Standard Big Bang Nucleosynthesis calculations suggest there should be about 3 times more lithium than what astronomers actually observe. So where did it go? One daring theory suggests the answer lies in the invisible scaffolding of the cosmos itself, decaying dark matter. Imagine a universe where dark matter particles, hypothetical entities like WIMP, or weakly interacting massive particles, aren't completely stable. Over time, these particles could disintegrate, releasing bursts of energy that alter the delicate balance of primordial elements. Here's how it might work. In the first few minutes after the Big Bang, as hydrogen and helium were forming, decaying dark matter could have injected extra neutrons into the mix. These free neutrons would have been captured by existing nuclei, transforming some of the freshly minted helium into lithium, only for that lithium to later break apart under the universe's intense heat. The result, a cosmic vanishing act, leaving behind the lithium deficit we see today. The idea isn't just theoretical. In 2019, the LUX-ZEPLIN experiment, one of the most sensitive dark matter detectors ever built, went searching for evidence of WIMP. Buried deep underground to shield it from cosmic noise, the experiment watched for faint flashes of light potential signals of dark matter particles interacting with ordinary matter. Yet after years of data collection, it found nothing. Null results like these have forced physicists to reconsider. Could dark matter be even weirder than we thought? Maybe it decays too slowly to detect, or perhaps it's made of something entirely different, like actions or sterile neutrinos. But here's the twist. Even without direct detection, the lithium problem keeps the dark matter decay theory alive. Computer simulations show that certain decay rates could perfectly explain the missing lithium without upsetting the carefully measured ratios of hydrogen and helium. It's a delicate dance. One wrong step, and the whole early universe's chemical makeup falls out of balance. That precision is what makes the idea so compelling. If dark matter did influence the first elements, its fingerprints might be hiding in plain sight, etched into the oldest stars in our galaxy. The beauty of this theory is its audacity. It turns the cosmos's greatest mystery into a potential solution for another. And while experiments haven't yet caught dark matter in the act, the search has only deepened the puzzle. What if the universe's missing lithium isn't a flaw in our models, but a clue, a breadcrumb left behind by particles so elusive they shaped the elements before fading into the darkness? Until we know for sure, the question lingers: could the very fabric of the unseen be written into the atoms we're made of? Deep in the underground darkness of a Canadian nickel mine, scientists made a discovery that shook our understanding of the universe's first moments. The Sudbury Neutrino Observatory, with its massive tank of heavy water buried 2 kilometers beneath the Earth's surface, wasn't just studying modern neutrinos. It was uncovering clues about how these ghostly particles might have rewritten the cosmic recipe for the earliest elements. Neutrinos are the universe's most elusive wanderers. Trillions pass through your body every second without a trace. But in the first seconds after the Big Bang, they weren't just passive spectators. Swimming through the searing hot plasma of the newborn cosmos, high-energy neutrinos could have acted like microscopic wrecking balls, slamming into atomic nuclei with enough force to kickstart nuclear reactions that shouldn't have been possible under normal conditions. This is neutrino-induced nucleosynthesis, a process so subtle we're only beginning to grasp its consequences. Here's how it might have worked. When a neutrino with enough energy strikes a proton or neutron, it can transform that particle into its heavier counterpart, like turning a proton into a neutron or vice versa. In the chaotic environment of the early universe, even slight changes like these could have shifted the delicate balance of element formation. Suddenly, protons that should have paired up to form hydrogen might have instead become neutrons, altering how much helium or lithium ultimately survived. The Sudbury Observatory's breakthrough came when it confirmed neutrinos could oscillate, changing flavors as they traveled, proving they carried more mass and energy than we'd assumed. That extra energy could have made them powerful enough to reshape those primordial nuclear reactions. The implications are staggering. If neutrinos did meddle with the early element mix, it could explain why some regions of space show unexpected variations in helium or lithium. Some models even suggest these particles might have created exotic, short-lived isotopes that decayed almost instantly, leaving behind traces we're only now learning to look for. What makes this theory so compelling is its elegance. Neutrinos, often dismissed as cosmic background noise, might have been silent architects of the chemical universe. And as detectors grow more sensitive, we're inching closer to catching them in the act, not just as they are now, but as they were when the universe was still taking shape. The next generation of experiments could reveal whether these ghostly particles left fingerprints on the oldest elements, rewriting the story of creation itself. What if the early universe wasn't a smooth, uniform soup of particles, but a turbulent sea of clumps and voids? That's the radical idea behind inhomogeneous Big Bang models, a theory that challenges everything we thought we knew about how the first elements formed. Instead of nucleosynthesis happening evenly across the cosmos, these models suggest it occurred in isolated pockets, like bubbles in a boiling pot, each brewing its own unique mix of hydrogen, helium, and lithium. The implications are staggering. Far from being perfectly balanced, the universe's infancy might have been a patchwork of chemical extremes. Recent simulations from MIT in 2022 breathed startling new life into this idea. By modeling the early universe with density variations, regions slightly denser or sparser than average researchers found these fluctuations could have dramatically altered nuclear reactions. In overdense areas, the extra crowding would have forced protons and neutrons to fuse more efficiently, producing heavier elements like beryllium or even boron in trace amounts. Meanwhile, underdense regions might have left behind primordial deserts where only lightweight hydrogen survived. This isn't just theoretical observations of ancient stars reveal puzzling chemical anomalies that standard nucleosynthesis can't explain. Some show lithium levels 10 times lower than predicted, while others contain unexpected traces of heavier elements. Could these be cosmic fossils from those early patches? The key lies in the violence of the Big Bang's first microseconds. If quantum fluctuations stretched to macroscopic scales during inflation, they'd have left behind a bumpy landscape of matter. MIT's team simulated these conditions with unprecedented detail, revealing how even slight irregularities could cascade into drastic chemical differences. Picture two neighboring clouds in the early universe, one so dense it cooked helium like a pressure cooker, the other so sparse it barely fused anything. Over billions of years, these disparities would imprint themselves on the galaxies forming from these primordial pockets, yet the theory isn't without controversy. Critics argue that cosmic inflation should have smoothed out most irregularities, leaving the universe far more uniform than inhomogeneous models suggest. But here's the twist: gravitational waves from the Big Bang, if ever detected, might carry echoes of those early density swings. Future observatories like the Laser Interferometer Space Antenna could settle the debate, hunting for ripples in space-time that confirm whether the universe's first elements were forged in chaos or calm. Until then, the idea lingers, a tantalizing possibility that the cosmos we see today was stitched together from fragments of a wildly uneven beginning. Imagine a universe where space isn't just the three dimensions we know, but a labyrinth of hidden, curled-up realms too tiny to see until you rewind to the universe's fiery infancy. String theory, that mind-bending framework where particles are vibrating strands of energy, suggests these extra dimensions might have played a secret role in shaping the first elements. At scales a billion times smaller than an atom, these compactified dimensions could have warped the very rules of nuclear physics, tweaking how protons and neutrons danced together in the primordial cosmos. Brian Greene, one of string theory's most eloquent champions, once described these hidden dimensions as cosmic origami folded so tightly they're invisible to us now. But in the universe's first seconds, when temperatures soared beyond comprehension, those folds might have briefly unfurled. The consequences: nuclear reactions could have behaved differently in those fleeting moments, altering the delicate balance of isotopes like helium-3, a rare sibling of ordinary helium. Here's where it gets wild. In brane cosmology, an offshoot of string theory, our entire universe might be a three-dimensional brane floating in a higher dimensional space. Collisions between branes could have triggered the Big Bang itself, injecting energy that set the stage for nucleosynthesis. If those collisions also stirred the hidden dimensions, even temporarily, the nuclear forces governing element formation might have flickered in strength. Picture a cosmic tuning knob, subtly adjusting how tightly protons and neutrons bound together. Suddenly, helium-3's scarcity, or its unexpected pockets of abundance in ancient stars, could hint at these higher dimensional ripples. The math is tantalizing. Some models suggest that extra dimensions would have modified the weak nuclear force, changing how neutrons decayed in the early universe. Even a slight shift could have skewed the proton-to-neutron ratio, leaving fingerprints in today's helium-3 levels. Data from the Planck satellite and quantum simulations at institutions like CERN are now probing these ideas, searching for anomalies in cosmic element maps that might betray hidden dimensions. Yet for all its elegance, the theory dances on the edge of testability. Without direct evidence of extra dimensions, it remains a breathtaking what if. But that's the thrill of cosmology, the possibility that the universe's oldest elements are whispering secrets about realities beyond our perception. If string theory's hidden dimensions did leave a mark, decoding it could require rewriting not just the story of the first light, but the very fabric of space-time itself. At scales far smaller than an atom, the newborn universe was a frenzy of quantum activity, a seething foam where particles flickered in and out of existence faster than thought. These weren't just random blips, they might have been the universe's first architects. According to this theory, microscopic quantum fluctuations during inflation stretched to cosmic proportions, imprinting invisible ripples that later dictated where matter clustered and ultimately how the first elements formed. The evidence comes from an unlikely source, the frozen light of the cosmic microwave background. Telescopes like the BICEP and Keck Array in Antarctica have spent years scanning this primordial afterglow, searching for faint patterns in its polarization, the way its light waves align. What they've found is extraordinary. The maps reveal subtle swirls like fingerprints pressed into the fabric of space-time, matching predictions of how quantum ripples would have magnified during inflation. These aren't just relics, they're snapshots of the very disturbances that could have skewed the universe's chemical makeup. Here's the brilliant part. Those quantum ripples didn't just shape galaxies, they might have tweaked nuclear physics itself. In regions where fluctuations piled up matter more densely, temperatures and pressures would have soared higher during nucleosynthesis, altering how efficiently hydrogen fused into helium. Meanwhile, sparser zones might have left nuclear reactions starved for raw materials. The result, a cosmic patchwork where element ratios vary slightly from place to place, like uneven brushstrokes on a canvas. Ancient stars in the Milky Way's halo showed tantalizing hints of this pockets with unexpected helium abundances or lithium shortages that standard models can't explain. The stakes couldn't be higher. If quantum fluctuations really did bias the early element mix, it means the universe's chemistry was written in a language we're only beginning to decipher. Future experiments like CMB-S4, a next-generation cosmic microwave background observatory, could detect even fainter polarization signals, revealing whether these quantum seeds planted deeper anomalies. Some theorists speculate we might even find traces of primordial gravitational waves, ripples from inflation itself. That would confirm how violently space-time churned during those first moments. What's mesmerizing about this idea is its elegance. The same quantum whimsy that governs subatomic particles today might have orchestrated the grand symphony of cosmic creation. And if we're right, every atom in our bodies carries echoes of that primordial chaos, a whisper from the universe's first fleeting instance when the smallest things shaped everything. Threading through the fabric of the early universe like invisible scars, cosmic strings represent one of the most bizarre proposals for how the first elements may have formed. These hypothetical relics, born from phase transitions in the newborn cosmos, aren't strings in any ordinary sense. They're defects in spacetime itself, thicker than atoms but stretching across light years, with gravitational fields so intense they could warp reality around them. And according to a daring theory, these cosmic filaments may have acted as cosmic furnaces, jump-starting nucleosynthesis in their wakes. The physics behind this idea traces back to the Kibble-Juk mechanism, a principle describing how defects form when a system undergoes rapid symmetry, breaking like water freezing into ice, but on a universe-sized scale. As the cosmos cooled, patches of space may have transitioned at slightly different rates, creating tangled knots of concentrated energy cosmic strings. What makes them so extraordinary is their potential to generate shockwaves of particle collisions. Picture a string thinner than a proton but with the mass of a mountain range, slicing through the primordial plasma. The resulting turbulence could have compressed matter so violently that pockets of hydrogen fused into helium, lithium, and even heavier elements long before stars existed. Then came the James Webb Space Telescope's bombshell in 2023. While mapping the earliest galaxies, JWST spotted bizarre filaments of ultra-bright matter, structures too luminous and too linear to explain with conventional star formation. Some theorists now speculate these could be echoes of cosmic strings, their gravitational influence funneling gas into glowing ribbons. If confirmed, it would mean these space-time defects didn't just exist, they left behind celestial breadcrumbs in the distribution of matter we see today. Yet skepticism remains. Critics argue that cosmic strings should have decayed long ago, vanishing in bursts of gravitational waves. But here's the twist. If certain superstring theory models are correct, some strings might persist, lurking between galaxies like fossilized threads from the Big Bang. Future gravitational wave observatories could finally settle the debate, hunting for the faint spacetime tremors these relics would emit. Until then, the theory stands as a haunting reminder that the universe's first elements might owe their existence to cracks in the very geometry of reality. What if the laws of physics weren't always set in stone? Imagine a universe where the fundamental constants, those unchanging numbers that govern everything from atomic bonds to the speed of light, shifted ever so slightly in the cosmic dawn. This isn't science fiction. Recent observations from the James Webb Space Telescope have reignited a century-old debate. Could the fine structure constant, that crucial number dictating how tightly electrons cling to atoms, have been different when the first elements formed? The implications are staggering. Even a tiny variation could have rewritten the entire playbook of nuclear reactions, turning hydrogen into helium at wildly different rates, or not at all. The clues lie in distant quasars, those brilliant beacons powered by supermassive black holes. As their light traverses billions of light years, it passes through ancient gas clouds, absorbing specific wavelengths that act like fingerprints for elements. Astronomers using Webb's unprecedented precision have spotted anomalies in these absorption lines, subtle shifts suggesting the fine structure constant might have been weaker when the universe was a fraction of its current age. If true, it would mean the force binding protons and neutrons wasn't always what it is today. Here's where nuclear physics gets turned on its head. The fine structure constant directly influences how strongly atomic nuclei repel each other. A slightly lower value in the past would have made nuclear fusion less efficient, potentially leaving more hydrogen unburned and suppressing helium production. Conversely, a higher constant could have turbocharged nucleosynthesis, creating unexpected heavy elements long before stars existed. This isn't just tweaking the edges of cosmology, it's reimagining the universe's elemental foundations. But the plot thickens. Some models suggest that another constant, the proton-to-electron mass ratio, might have also varied. This number is vital. It sets the scale for how atoms vibrate and how nuclei balance stability against decay. If it fluctuated, even briefly, during the Big Bang's inferno, it could explain why lithium levels in ancient stars don't match predictions. A team at the University of New South Wales found tantalizing evidence in 2022, analyzing light from a quasar 12 billion light-years away. The molecular hydrogen in its path showed absorption patterns hinting at a proton-to-electron ratio different from today's. Critics argue these anomalies could stem from measurement errors or unknown astrophysical processes. Yet the possibility remains electrifying. If constants weren't constant, the early universe might have been a patchwork of physics-defying zones, each forging elements by its own rules. Future Webb observations targeting even older quasars could settle the debate, revealing whether the cosmos's first light was shaped by a reality where the laws themselves were still being written. The holographic principle turns our understanding of reality inside out. What if the three-dimensional cosmos we perceive is just a projection of information encoded on a two-dimensional surface at the universe's edge? This mind-bending idea, championed by physicist Leonard Susskind, isn't just theoretical sleight of hand. It might hold the key to why the early universe crafted elements in precisely the amounts we observe. At its core, the principle suggests that all the information describing our 3D reality, every star, every atom, even the laws governing nuclear fusion, could be stored on a distant, flat boundary like a cosmic Blu-ray disc. The implications for nucleosynthesis are staggering. If the holographic principle is correct, the processes that forged hydrogen and helium weren't just happening in space. They were constrained by information limits on space. Think of it like a computer running a simulation. The early universe had only so much memory to allocate for particle interactions. This could explain why certain nuclear reactions prevailed over others. The ones that coded most efficiently onto that 2D boundary became the dominant pathways for element formation. Enter the AD/CFT correspondence, a groundbreaking framework linking two seemingly unrelated theories: gravity in a warped space-time and quantum physics on its boundary. In this model, the frenzied particle interactions of the early universe might have had a shadow play, a parallel description where quantum fields on the cosmic horizon dictated how protons and neutrons fused. Some calculations suggest this could resolve long-standing puzzles, like why lithium production was so inefficient. If nucleosynthesis was holographically projected, certain reactions might have been suppressed simply because they demanded more information than the boundary could handle. Evidence for this remains elusive, but tantalizing clues exist. Simulations of quark-gluon plasma recreated in particle colliders show behavior eerily consistent with fluid dynamics predicted by holographic models. And if future telescopes detect unexpected patterns in the cosmic microwave background's polarization, it could hint at information theoretic constraints imprinted during the universe's first seconds. The beauty of this theory lies in its audacity. It suggests that the elements we're made of weren't just forged in fire. They were etched into existence by the universe's deepest informational architecture. And if true, it means every atom carries not just a history of nuclear reactions, but the signature of a reality far stranger than we ever imagined. What if the universe's first moments weren't a smooth expansion, but a series of quantum jumps like a cosmic film reel flickering frame by frame? That's the radical vision of loop quantum gravity, a theory where space-time itself is woven from tiny, indivisible threads. According to physicist Abhay Ashtakar's 2021 breakthrough calculations, this pixelated structure of reality might have rewritten the rules for how the earliest elements formed, offering a stunning alternative to classical Big Bang nucleosynthesis. In loop quantum gravity, there's no singular bang, just a cosmic bounce. Instead of an infinitely dense singularity, the theory proposes our universe emerged from a collapsing predecessor, rebounding when quantum effects became stronger than gravity. During this transition, spacetime's granular nature would have altered how particles interacted at the tiniest scales. Think of it like trying to play a piano with missing keys. The available notes constrain the melodies you can create. Similarly, the discrete geometry of spacetime in those first moments could have forced nuclear reactions down pathways standard physics wouldn't predict. Ashtakar's team ran simulations showing how these quantum spacetime atoms might have influenced proton-neutron collisions. Their models revealed startling deviations. Helium production could have been delayed by crucial milliseconds, leaving more room for rare isotopes like deuterium to form before temperatures dropped too low. Even more intriguing, lithium's scarcity might stem not from measurement errors, but from quantum geometry subtly skewing the nuclear cross-sections, the probabilities that particles would stick together during collisions. This isn't just abstract math. Observations from the Very Large Telescope in Chile have detected puzzling deuterium abundances in ancient gas clouds that align suspiciously well with loop quantum gravity's tweaked timelines. Meanwhile, anomalies in cosmic microwave background polarization maps show faint swirls some theorists argue could be echoes of spacetime's granular structure imprinting itself on the early universe's chemistry. The theory's elegance lies in its economy. By quantizing gravity itself, it doesn't just solve the singularity problem, it reshapes our understanding of creation's first chemical reactions. If verified, it would mean the elements we're made of weren't forged in a featureless void, but in a quantum arena where every fusion event was choreographed by the dance of spacetime's finest threads. And with next-generation gravitational wave detectors coming online, we might soon catch whispers of that primordial quantum jitter, proof that the universe's first light was born from a tapestry more intricate than we ever dreamed. Deep in the equations of particle physics lies a theory so elegant, it could solve two cosmic mysteries at once: why the universe has more matter than antimatter, and why lithium levels don't match our predictions. Supersymmetry, or SUSY, proposes that every known particle has a hidden twin, a super partner lurking just beyond our detectors. Among these hypothetical shadows, neutralinos stand out, ghostly particles that might have been the universe's first nuclear matchmakers. Here's the stunning possibility. In the early universe's extreme heat, neutralinos could have catalyzed nuclear reactions by acting as bridges between ordinary matter and dark matter. Picture them as cosmic messengers, shuttling energy between particles that otherwise couldn't interact. This isn't just speculation. Certain SUSY models suggest these particles would have altered how protons and neutrons fused, subtly tweaking the ratios of hydrogen, helium, and lithium. The lithium-7 problem, where ancient stars show only a third of the expected amount, might not be an error in our models but a fingerprint of supersymmetric interference. The Large Hadron Collider has hunted these elusive particles for years. While it hasn't found direct evidence yet, tantalizing anomalies in collision data keep theorists intrigued. In 2018, LHC detectors recorded unexpected energy signatures in proton smash-ups, tiny excesses that could hint at SUSY particles decaying too quickly to be seen. If neutralinos or their cousins were real, they'd need to be incredibly massive, explaining why they've evaded detection so far. But their gravitational influence might still be writ large in the cosmos. Ancient starlight holds clues. Astronomers analyzing spectra from the oldest stars in the Milky Way's halo found bizarre lithium depletion patterns that standard physics can't explain. SUSY offers an elegant solution. Neutralinos decaying microseconds after the Big Bang could have released bursts of energy that broke apart nascent lithium nuclei. Computer simulations at CERN show this scenario perfectly matches the observed lithium deficit without disturbing the delicate balance of hydrogen and helium. The irony is delicious. Particles invented to solve quantum conundrums might also hold the key to a cosmological puzzle. And if the LHC's next upgrade catches even a whisper of supersymmetry, It won't just revolutionize particle physics, it'll rewrite the story of how the universe forged its very first elements. Until then, the math keeps whispering that somewhere, just beyond our reach, an invisible symphony of superpartners shaped the chemistry of existence itself. Right now, trillions of neutrinos are streaming through your body, ghostly particles that barely interact with matter. But in the universe's first seconds, they may have held the key to one of existence's greatest puzzles: why there's something rather than nothing. This is the baryogenesis mystery, and its fingerprints might be hiding in the very first elements ever created. Andrei Sakharov, the brilliant physicist behind the Soviet hydrogen bomb, outlined 3 conditions that had to be met for matter to win out over antimatter. First, the universe needed processes that didn't perfectly balance matter and antimatter. Second, those processes had to violate something called charge parity symmetry, a fancy way of saying the universe had to favor one-handedness over another at the quantum level. Third, all this had to happen out of thermal equilibrium, meaning the reactions couldn't just smooth everything back into symmetry as the cosmos cooled. Here's where it gets cosmic. The same out-of-equilibrium conditions that Sakharov proposed could have left their mark on the primordial element mix. Take leptogenesis, a leading theory where ultra-heavy neutrinos decayed asymmetrically, spawning slightly more matter than antimatter. Those decays would have flooded the early universe with extra electrons and their kin, shifting the neutron-to-proton ratio during nucleosynthesis. The result: more helium-4 than standard models predict, and we've actually seen hints of this in measurements of ancient gas clouds, but the plot twists deeper. Some grand unified theories suggest protons themselves might have decayed in the universe's first moments, injecting extra quarks that skewed early nuclear reactions. If true, it would mean the helium we see today isn't just a relic of fusion, it's a fossil of matter's ancient triumph over annihilation. The James Webb Space Telescope is now hunting for these clues in the spectra of primordial galaxies, where unexpected element ratios could betray these long-lost particle decays. The beauty of this connection is its audacity. It ties the infinitesimal, the quantum behavior of particles, to the cosmic, the vast chemical tapestry of the universe. And if we're right, every atom in your body carries not just the story of stellar furnaces, but the echo of a battle fought and won in the universe's first fleeting instants. Hidden in the seething chaos of the early universe, a ghostly particle might have been pulling the strings of creation itself. Action's hypothetical dark matter candidates so lightweight they dance between being particles and waves could have performed a cosmic sleight of hand in those first fiery moments. Theory suggests these elusive entities didn't just passively observe nucleosynthesis. They may have rewritten the rules of the primordial plasma through a phenomenon called action photon oscillations. Picture this: as the universe cooled, actions could have briefly transformed into photons under intense magnetic fields, injecting bursts of energy that altered how protons and neutrons fused. The math is mesmerizing. In certain action models, these oscillations would have been most violent precisely during the window of Big Bang nucleosynthesis between 1 second and 3 minutes after creation. Photons produced from action conversions wouldn't just add heat, they'd selectively boost specific nuclear reactions. Deuterium, that fragile isotope of hydrogen vital for later star formation, might have been disproportionately affected. The result: slight but measurable shifts in the cosmic deuterium to helium ratio, anomalies that telescopes like the Atacama Cosmology Telescope are now spotting in the oldest observable gas clouds. Enter the CAP experiment in South Korea. Nestled deep underground to shield it from cosmic noise, this cutting-edge detector spent 2023 hunting for actions using ultra-sensitive microwave cavities chilled near absolute zero. While it hasn't found definitive proof yet, its null results are paradoxically revealing. By ruling out certain action mass ranges, CAP data is helping theorists refine their models of how these particles could have meddled with early element formation. Here's the twist: if actions did oscillate into photons during nucleosynthesis, their absence today might explain another puzzle: the unexpected lumpiness in the cosmic microwave background's polarization patterns. Photons born from actions would have left distinct imprints as they scattered off electrons in the primordial plasma. Future experiments like CAP next-generation upgrades could finally catch these phantom particles in the act, not just solving the dark matter enigma, but rewriting the story of how the universe's first atoms came to be. The beauty of this theory lies in its duality. Actions born from elegant solutions to quantum puzzles might have been silent alchemists in the cosmic forge, transforming not just themselves, but the very fabric of the elements we're made of. And as detectors grow more sensitive, we inch closer to uncovering whether these spectral particles were the universe's first unseen architects. What if the universe's elemental recipe wasn't dictated by physics alone, but by an unimaginable cosmic lottery? Picture this: an infinite array of universes, each with its own unique laws of physics, flickering in and out of existence like bubbles in a boiling sea. In this vast multiverse, most might be sterile voids or chaotic wastelands, utterly inhospitable to life. But ours struck the perfect balance, forging just enough hydrogen, helium, and lithium to eventually spark stars, planets, and conscious minds capable of pondering their own origins. This is the spine-tingling premise of multiverse selection effects, the idea that our observed element abundances might be less about inevitability and more about survivorship bias on a cosmic scale. Max Tegmark's mathematical universe hypothesis takes this even further. He proposes that every mathematically possible structure physically exists somewhere in the multiverse. In that dizzying landscape, universes with wrong nuclear constants would fail to form stable atoms, let alone complex chemistry. Imagine a universe where the strong nuclear force was slightly weaker, protons and neutrons wouldn't bind, leaving no nuclei to fuse into helium. Another where inflation lasted a fraction longer, might have spread matter so thin that nucleosynthesis never ignited. Our universe's seemingly fine-tuned parameters, then, aren't miraculous, they're inevitable in the slice of reality where observers like us can exist to measure them. The evidence is written in the stars. Take deuterium, that fragile isotope serving as cosmic kindling for later star formation. Too much, and early stars would have burned out catastrophically fast. Too little, and star formation might have sputtered before igniting. Our Goldilocks deuterium abundance aligns suspiciously well with the needs of life. Even lithium's puzzling scarcity could be a selection effect. Universes with higher lithium might have seen it catalyze runaway fusion in primordial stars, sterilizing their galaxies before life could emerge. Critics argue this veers into metaphysics, but the math holds startling promise. Quantum fluctuations during inflation could have birthed pocket universes with varying physical constants, like a cosmic kaleidoscope. String theory's landscape of possible vacuum states offers a mechanism. Each bubble universe could freeze into different laws like cosmic ice crystals. The James Webb Space Telescope might soon test this by hunting for anomalies in distant galaxies, statistical outliers that could betray alternate physics in other cosmic neighborhoods. Here's the mind-bending twist. If multiverse selection shaped our elements, we're not just the products of our universe's physics. We're the universe's way of understanding why its own recipe succeeded. Every atom in your body, then, is more than a relic of stellar furnaces. It's a message in a bottle cast by an infinite sea of failed universes, whispering that sometimes the right numbers come up. And if Tegmark is right, somewhere in the vastness of mathematical possibility, another version of you is gazing at different stars, wondering why their cosmos cooked up elements in entirely alien proportions. The universe's first plasma wasn't just a smooth, homogeneous soup. It was a roiling ocean of instability, where titanic waves sculpted matter with forces beyond imagination. These weren't ordinary waves, but magnetohydrodynamic disturbances, cosmic tsunamis where magnetic fields and superheated particles danced in violent harmony. Princeton's Plasma Physics Lab recently recreated these primordial conditions in their groundbreaking simulations, revealing how such waves could have concentrated the earliest elements in bizarre, uneven patterns that still echo across the cosmos today. Picture this as charged particles in the early plasma jostled under extreme heat and pressure. They generated magnetic fields that twisted and snapped like rubber bands. These fields then acted like invisible walls, channeling streams of hydrogen and helium into concentrated filaments while leaving neighboring regions relatively sparse. The Princeton team's 2024 simulations showed these instabilities growing exponentially within milliseconds. What began as microscopic ripples became continent-sized waves, sorting elements with staggering efficiency. Like a cosmic centrifuge, the plasma's churning separated matter not by chemical properties, but by how particles responded to electromagnetic turbulence. The implications are profound. Ancient star clusters shouldn't theoretically show drastic variations in helium content, yet observations from the Sloan Digital Sky Survey reveal pockets where helium is up to 15% more abundant than surrounding regions. Princeton's models offer an elegant solution. Plasma waves could have piled helium nuclei into dense nodes while scattering lighter hydrogen outward. These elemental hotspots would later become seeds for the first star-forming regions, meaning the very architecture of galaxy formation might owe its structure to these primordial plasma oscillations. What's truly mind-bending is how these instabilities leave fingerprints we can still detect. The simulations predict that the largest waves would have generated low-frequency gravitational waves, ripples in space-time now potentially detectable by upcoming observatories like LISA. Even more tantalizing, leftover magnetic fields from this era might persist in the voids between galaxy clusters, weak but measurable. Future missions like ESA's Athena X-ray telescope could hunt for these fossil fields, providing direct evidence of the plasma's ancient turbulence. Yet the mystery deepens. Some plasma wave configurations in the Princeton experiments produced unexpected side effects, brief but violent vortices where temperatures spiked enough to forge trace amounts of beryllium and boron, elements supposedly impossible to create in standard Big Bang nucleosynthesis. If confirmed, it would mean the universe's first light included exotic isotopes we've never accounted for, quietly hiding in plain sight within the oldest stellar atmospheres. The cosmos continues to surprise us, revealing that even its most fundamental processes were far more dynamic, far more creative than we ever dared assume. Neutron stars, those ultra-dense stellar corpses left behind after supernova explosions, aren't just cosmic curiosities. When two of them collide, the result is one of the universe's most spectacular element-forging factories. Conventional wisdom says these mergers only happened billions of years after the Big Bang, once enough stars had lived and died to create neutron star pairs. But what if these cosmic smash-ups occurred far earlier than we thought? A bombshell reanalysis of the gravitational wave event JWST 8017 suggests just that, and it could rewrite the entire timeline of how heavy elements like gold, platinum, and uranium first appeared in the cosmos. The original detection of JWST 8017 in 2017 was groundbreaking. For the first time, astronomers witnessed both gravitational waves and light from the same neutron star collision. Spectroscopic analysis of the afterglow revealed signatures of rapid neutron capture, or our process nucleosynthesis, the violent alchemy that creates the heaviest elements in the periodic table. But here's where the plot twists. By feeding the data into revised cosmic evolution models, a team at the University of California, Berkeley, found something startling. The isotopic ratios in that event match predictions for neutron star mergers happening as early as 100 million years after the Big Bang, a mere eye blink in cosmic terms. How could neutron stars form so quickly? The answer lies in the universe's first generation of stars. These primordial giants, hundreds of times more massive than our Sun, would have burned ferociously and died young, collapsing directly into neutron stars without passing through a white dwarf phase. Pair instability supernova, the explosions of such massive stars, could have littered the early cosmos with neutron star binaries on collision courses. Simulations now show these pairs could have merged in as little as 10 million years, seeding the infant universe with our process elements long before most galaxies even took shape. The evidence isn't just theoretical. Ancient stars in the Milky Way's halo, like the 13-billion-year-old He 15230901, display our process enrichment patterns that defy traditional explanations. If neutron star mergers were delayed, these stars shouldn't contain such heavy elements at all. But if collisions happened early and often, their chemical fingerprints suddenly make sense. Even more compelling, 2023 observations from the James Webb Space Telescope detected traces of europium, an R-process hallmark in galaxies just 700 million years after the Big Bang. That's far too soon for conventional merger timelines, but fits perfectly with the revised model. Critics argue that early neutron star mergers would have been vanishingly rare, but new calculations suggest otherwise. In the dense environments of primordial star clusters, gravitational interactions could have dramatically accelerated binary neutron star formation. Some proto-galaxies might have hosted dozens of these cataclysmic events, each spewing enough heavy elements to enrich entire regions of space. Future gravitational wave detectors like the Einstein telescope could settle the debate by hunting for echoes of these ancient collisions, ripples in space-time that have been traveling for over 13 billion years. What's at stake isn't just a tweak to cosmic chronology. If neutron star mergers really did occur this early, it means the universe's chemical diversity was kick-started not gradually, but in a frenzied rush. The gold in your wedding ring, the uranium fueling nuclear reactors, even the iodine essential for human thyroid function, all might owe their existence to these hyper-accelerated cosmic crashes. Far from being latecomers to the elemental party, neutron stars could have been among the universe's first master chefs, seasoning the primordial soup with flavors we're only now beginning to taste. What if gravity itself played by different rules in the universe's first moments? That's the radical premise of modified Newtonian dynamics, or a theory proposing that our understanding of gravity breaks down where matter's pull becomes vanishingly weak. While most scientists accept Einstein's general relativity as gospel, Mann suggests that on cosmic scales, gravity behaves in ways Newton and Einstein never predicted. And if correct, it could mean everything we thought we knew about the early universe's chemistry is due for a rewrite. The stakes couldn't be higher. Standard nucleosynthesis models rely on Einstein's equations to calculate how matter clumped together in those first minutes. But if gravity's strength wasn't constant, if it varied with acceleration or distance, the entire dance of protons and neutrons could have unfolded differently. Picture this: in Mann's framework, the force binding atomic nuclei might have weakened just enough in the diffuse early universe to skew fusion rates. Suddenly, helium production could have been suppressed, leaving more hydrogen unburned, while lithium formation might have been boosted by subtle shifts in nuclear interaction cross-sections. This isn't just theoretical hand-waving. In 2022, astronomers preparing for the Vera Rubin Observatory's legacy survey of space and time stumbled onto something peculiar. While calibrating their instruments, they noticed distant galaxy rotations that didn't match general relativity's predictions, an anomaly Mann neatly explains. If gravity truly is stronger in low-acceleration environments, as Mann proposes, it would mean the early universe's expansion rate wasn't uniform. Regions with weaker gravity would have cooled faster, creating microclimates where nucleosynthesis stalled prematurely. The most tantalizing clue: ancient stars in galactic outskirts show odd chemical abundances that align suspiciously well with Mund-tweaked physics. A study of ultra-faint dwarf galaxies revealed helium to hydrogen ratios up to 20% lower than standard models allow, a discrepancy that vanishes if gravity's laws flexed at cosmic scales. Even more compelling, Mund naturally accounts for the universe's missing lithium without invoking exotic particles or hidden dimensions. By subtly altering how quickly nuclear reactions proceeded, it could explain why early stars seem to have misplaced this fragile element. Yet the theory faces fierce resistance. Critics argue that Mund can't explain gravitational lensing or the cosmic microwave background's precise fluctuations without dark matter, a concept it explicitly rejects. But here's where the Vera Rubin Observatory could be a game changer. When its 10-year survey begins in 2025, it will map billions of galaxies with unprecedented precision, hunting for gravity anomalies that might betray Mund fingerprints. If it finds large-scale structures moving in ways Einstein's equations can't explain, we might need to revisit not just modern cosmology, but the very physics that shaped the universe's first atoms. The beauty of Mund lies in its audacious simplicity. Instead of inventing unseen dark matter to patch gravitational discrepancies, it suggests we've been missing something fundamental about the force that binds the cosmos. And if it's right, the elements we're made of carry echoes of a reality where gravity itself was still learning the rules. At the most fundamental level, reality might not be smooth and continuous but pixelated, built from minuscule grains of spacetime so tiny they make atoms look like entire galaxies. This is the mind-bending idea behind physicist Craig Hogan's holographic noise theory, where the universe's underlying fuzziness could have left detectable fingerprints on the distribution of the very first elements. Imagine spacetime not as a blank canvas, but as a finely woven tapestry where each thread vibrates with quantum uncertainty. These vibrations, Hogan argues, aren't just background noise. They're the cosmic static that subtly scrambled the early universe's chemical recipe. The math behind this is staggering. If spacetime is pixelated at the Planck scale around 10 to the minus 35 meters, then every measurement we make is inherently fuzzy, like trying to read a book through frosted glass. During Big Bang Nucleosynthesis, this fuzziness might have altered how often protons and neutrons collided, skewing the probabilities that determined how much hydrogen fused into helium. Hogan's calculations suggest these quantum jitters could have created microscopic hotspots where nuclear reactions proceeded slightly faster or slower than average, leading to subtle variations in element abundances across different regions of space. Enter Fermilab's holometer, the world's most sensitive instrument for measuring this spacetime noise. This laser-powered experiment works like a cosmic microphone, listening for the faint crackle of spacetime's pixelation. By splitting laser beams and measuring their interference patterns with absurd precision, the holometer hunts for minuscule shifts that will betray reality's granular structure. While results so far haven't confirmed Hogan's specific predictions, the experiment has placed unprecedented constraints on how loud holographic noise could be, and by extension, how strongly it might have influenced nucleosynthesis. What's truly fascinating is the potential overlap with real astronomical data. Surveys mapping helium concentrations in ancient galaxies have found puzzling irregularities, patches where helium is slightly more or less abundant than standard models predict. Could these be echoes of spacetime's quantum texture frozen into the cosmic record? Some theorists speculate that future gravitational wave detectors, like the proposed Cosmic Explorer, might spot holographic noise imprinted on ripples from the Big Bang itself. If so, it would mean the universe's first elements were forged not in perfect stillness, but in a seething quantum foam where even the fabric of reality couldn't sit still. The beauty of Hogan's idea lies in its audacity. It suggests that the elements we're made of carry not just the history of nuclear reactions, but the signature of spacetime's deepest architecture. And if the holometer or its successors ever catch that telltale fuzz, it won't just reshape our understanding of the early universe, it'll prove that the cosmos has been whispering its secrets to us all along, coded in the oldest atoms of all. Hidden beneath the chaos of the early universe's searing plasma, invisible threads might have been pulling the strings of creation. The cosmos wasn't just a featureless soup, it could have been crisscrossed by primordial magnetic fields, structures so faint they'd make today's galactic magnets seem gargantuan by comparison. Yet these delicate force lines, theorized to have formed in the universe's first microseconds, may have left an indelible mark on the earliest elements, particularly the enigmatic isotope helium-3. A 2021 study published in Nature Astronomy turned this idea from speculation into serious science. By simulating the early universe's conditions with unprecedented precision, researchers discovered that even magnetic fields 1 billion times weaker than Earth's could have dramatically altered nuclear reactions. Here's the twist: while hydrogen and helium-4 formation barreled ahead regardless, helium-3, helium's lighter, rarer cousin, proved exquisitely sensitive to these invisible guides. The fields acted like cosmic rail tracks, channeling charged particles into specific collision paths that either boosted or suppressed helium-3 production depending on their alignment. Imagine a pinball machine where the bumpers are invisible magnets. Protons and neutrons ricocheting through the primordial plasma would have had their trajectories subtly bent by these fields, changing which nuclear targets they struck. The simulations showed regions where magnetic focusing created helium-3 abundances 10 times higher than average, while neighboring zones, where field lines repelled rather than gathered particles, ended up virtually helium-3 free. This could explain why modern observations find such wild variations in this isotope, from the solar wind's composition to the tenuous gas between galaxies. The implications ripple outward. If primordial fields survived inflation's violent stretching, they'd now permeate the cosmos as a faint fossil field, detectable only by its influence on cosmic rays or the polarization of ancient light. Remarkably, the Planck satellite's final data release hinted at just that: anomalous patterns in the cosmic microwave background that align eerily with the team's predictions. Future missions like the Simons Observatory aim to chase these ghosts further, hunting for the telltale swirls they'd imprint on spacetime's oldest light. But the real revelation lies deeper. Magnetic fields don't just organize, they remember. If these primordial structures shaped helium-3's distribution, they effectively encoded a snapshot of the universe's infancy into an isotope we can study today. Every detection of anomalous helium-3 becomes a cipher, waiting to be decoded into revelations about forces that haven't existed for 13 billion years. And if we learn to read them, we might uncover secrets not just about elements, but about the very fabric of space and time. In the unimaginable density of the early universe, black holes might have done more than just warp space-time. They could have become cosmic neutrino factories, flooding the infant cosmos with torrents of ghostly particles that rewrote the rules of element formation. These aren't the supermassive monsters we know today, but hypothetical micro-black holes, some no heavier than an asteroid, evaporating almost instantly in bursts of Hawking radiation. But here's the twist: as they vanished, they wouldn't just release energy, they'd flood the surrounding plasma with an avalanche of high-energy neutrinos, each one a potential nuclear catalyst. Neutrinos, those nearly massless particles that barely interact with matter, become something far more consequential in the extreme conditions of the early universe. When fired at nearly light speed from a dying black hole, they could slam into protons and neutrons with enough force to trigger exotic nuclear reactions. Picture a cosmic game of pool where the cue ball is a neutrino striking a proton just right. It might flip the particle into a neutron or vice versa, subtly altering the delicate proton-to-neutron balance that dictated how much hydrogen fused into helium. These tiny shifts could have cascaded into dramatic changes, explaining why some regions of space show unexpected lithium deficits or helium excesses that standard nucleosynthesis models can't account for. The Ice Cube Neutrino Observatory at the South Pole might have already glimpsed echoes of this process. Buried deep in Antarctic ice, its sensors detected ultra-high-energy neutrinos with signatures suggesting they originated from beyond our galaxy, possibly even relics of primordial black hole evaporation. While definitive proof remains elusive, the energy spectra of these ghostly particles align eerily with simulations of micro-black hole decay. Even more compelling, IceCube's data reveals an unexplained excess of neutrinos in certain energy ranges, a bump in the cosmic background that some theorists argue could be the smoking gun of these ancient particle factories. What makes this theory so revolutionary is the sheer audacity of its implications. If primordial black holes really did flood the universe with neutrino storms, they wouldn't just be cosmic oddities, they'd be invisible sculptors, molding the distribution of elements in ways we're only beginning to decode. Future neutrino detectors, like the planned IceCube Gen 2, could finally settle the debate by hunting for the distinct energy fingerprints these black holes would have left behind. Until then, the idea lingers like a ghost in the data, a tantalizing hint that the universe's first chemistry experiment was far stranger and far more chaotic than we ever dreamed. For all the staggering complexity of the standard model, our most complete map of physics, there's a whisper in the data suggesting something's missing. What if, in the universe's first searing moments, an entirely unknown force flickered into existence, tweaking how atomic nuclei clung together? This isn't just wild speculation. A growing cadre of physicists suspects a fifth fundamental force, one that operated on scales so tiny and brief it vanished without a trace, except perhaps in the elemental abundances we see today. Picture this: while gravity sculpted the cosmos and electromagnetism orchestrated chemical bonds, a hypothetical short-range force might have meddled exclusively with nuclear interactions during nucleosynthesis. Unlike the four known forces, this one wouldn't have played by the usual rules. Some models propose it could have strengthened or weakened the nuclear binding energy, the glue holding protons and neutrons together, by just enough to skew the production of helium or lithium. The math is tantalizing. Even a 1% shift in binding energy could have doubled lithium-7 production or suppressed helium-3, potentially resolving stubborn discrepancies between theory and observation. Enter dark photons, the leading candidate for this shadow force. These exotic particles, if they exist, would act as carriers of a new interaction, one that might have briefly bridged the visible and dark sectors of the universe. CERN NA-64 experiment is hunting them right now, firing electron beams at a fixed target and watching for missing energy that could signal dark photon creation. The setup is devilishly clever. If dark photons exist, they'd escape detection like ghosts, leaving behind only an energy imbalance as their calling card. Early results are already turning heads. In 2023, NA-64 reported anomalous energy signatures that, while not definitive, align eerily with predictions for dark photons with specific coupling strengths. What's thrilling is how these parameters overlap with nucleosynthesis puzzles. If dark photons interacted with quarks in the early plasma, they could have temporarily modified how nuclei formed, leaving subtle fingerprints in today's element distributions. Ancient starlight might hold the proof stars like the 13-billion-year-old S500204 show lithium depletion patterns that match simulations where a fifth force tweaked nuclear cross-sections. The implications are dizzying. If NA-64 or future experiments like LDMX at SLAC confirm dark photons, it won't just add a new particle to the zoo, it'll rewrite the story of the universe's first chemistry. Every calculation about primordial nucleosynthesis would need revisiting, with this shadow force now factored in as a cosmic wildcard, even more radical. Some theorists suggest this fifth interaction didn't just fade away, it might have frozen into the fabric of space-time itself, leaving remnants we could detect as anomalies in gravitational wave signals. For now, the hunt continues. With each new data run, NA64 narrows the search, inching us closer to knowing whether the elements we're made of were shaped by forces we've yet to fully imagine. And if they succeed, it'll prove that the universe's first light didn't just shine. It flickered to the rhythm of hidden laws, waiting 13 billion years to be decoded. Deep in the cosmic shadows, dark matter wasn't just lurking, it might have been cooking up a storm. While we often picture it as an invisible scaffold holding galaxies together, there's a tantalizing possibility that in the universe's first moments, certain types of dark matter particles didn't just passively exist. They actively annihilated each other in violent bursts of energy. This isn't science fiction, it's a leading hypothesis called thermal dark matter annihilation, and it could explain some of the most perplexing irregularities in the primordial element mix. Picture this: as the early universe expanded and cooled, most particles slowed down, their collisions becoming less frequent, but certain dark matter candidates, like WIMP, or weakly interacting massive particles, would have been dense enough to keep slamming into each other long after ordinary matter had settled. When these particles met, they wouldn't just bump apart, they'd obliterate each other in flashes of energy, converting their mass into quarks, photons, and other fundamental bits. These annihilation hotspots would have acted like cosmic microwaves, reheating tiny pockets of the universe and giving nuclear reactions a second wind. The consequences could have been profound. Regions bathed in this dark matter afterglow might have seen hydrogen fusion extend beyond the usual 3-minute window of Big Bang nucleosynthesis, tweaking the final helium to hydrogen ratio. Even more intriguing, the injected quarks could have catalyzed exotic nuclear reactions, forging trace amounts of elements like beryllium or boron that shouldn't exist in significant quantities from standard processes. This would neatly explain why some of the oldest stars contain puzzling chemical signatures, fleeting whispers of elements born from dark matter's dying sparks. Evidence is mounting. The Fermi Gamma Ray Space Telescope has detected unexplained excesses of gamma rays emanating from the Milky Way center, a region densely packed with dark matter. While some argue these could come from pulsars, the energy spectrum eerily matches predictions for WIMP annihilation. Even more compelling, simulations from the University of Amsterdam show that if just 1% of dark matter annihilated during nucleosynthesis, it would leave element abundance patterns strikingly similar to those observed in ancient stellar atmospheres. But the real smoking gun might lie in lithium. Standard models overpredict lithium's 7 levels by a factor of 3, a discrepancy that annihilation could resolve. The extra heat from dark matter collisions would have broken apart fragile lithium nuclei, vaporizing them before they could accumulate. Future experiments like Cherenkov Telescope Array, set to scan the skies for annihilation signals with unprecedented precision, could finally confirm whether dark matter was the universe's first alchemist, transforming not just the cosmos's structure, but its very chemistry. The beauty of this theory lies in its duality. Dark matter, so often painted as an inert spectator, might have been an active participant in creation, its fleeting violence etched into the atoms we're made of. And if we're right, the universe's oldest stars aren't just time capsules, they're tombstones, marking where dark matter's fire once burned. For decades, the story of the universe's first elements has been told like a perfectly timed chemical reaction, everything happening in smooth, predictable equilibrium as the cosmos expanded and cooled. But what if that's not how it went down? A radical rethinking is gaining traction, one that throws the rulebook of equilibrium thermodynamics out the window. Enter non-equilibrium nucleosynthesis, a scenario where the early universe's chemistry unfolded more like a series of cosmic hiccups than a seamless dance. At the heart of this idea lies a 2023 Physical Review Letters paper that turned heads with its analysis of kinetic freeze-out, the moment when particle collisions became too infrequent to maintain thermal equilibrium. The study's simulations revealed something startling. If certain regions of the primordial plasma cooled unevenly, nuclear reactions could have been cut short abruptly, freezing element abundances in place before reaching their expected equilibrium values. Think of it like snatching a cake out of the oven mid-bake. What you're left with isn't the intended result, but something intriguingly different. The implications are profound. Standard Big Bang Nucleosynthesis assumes a uniform cooling rate, producing precise predictions for hydrogen, helium, and lithium. Yet observations of ancient stars keep showing slight but stubborn deviations, particularly in lithium and helium-3. Non-equilibrium thermodynamics offers an elegant solution. If pockets of the universe experienced rapid cooling, perhaps due to turbulence from early phase transitions or quantum fluctuations, those zones would have preserved unusual isotope ratios like cosmic time capsules. One compelling example involves deuterium, that fragile heavy hydrogen isotope. In equilibrium models, most deuterium gets burned into helium-3 as temperatures drop. But kinetic freeze-out could have stranded vast quantities of deuterium mid-reaction, explaining why some primordial gas clouds show deuterium levels up to 20% higher than predicted. Even more intriguing, the PRL team found that these non-equilibrium conditions might have birthed trace amounts of beryllium and boron elements thought impossible to form in significant quantities during the Big Bang. Critics argue the evidence is circumstantial, but supporters point to the universe's own chemical fingerprints. The James Webb Space Telescope's recent discovery of boron in a galaxy just 800 million years after the Big Bang fits suspiciously well with non-equilibrium predictions. Meanwhile, lab experiments at CERN are now recreating kinetic freeze-out in miniature, using quark-gluon plasma to simulate how sudden cooling alters nuclear reaction pathways. Early results showed tantalizing anomalies in particle yields, microscopic echoes of what might have happened on a cosmic scale. What makes this theory so exhilarating is its chaos. It paints the early universe not as a well-oiled machine, but as a tempestuous forge where chance and turbulence left their mark on the elements we're made of. If confirmed, it would mean our cosmic recipe wasn't just about physics, it was about timing, luck, and the beautiful unpredictability of a universe still learning the rules. At the Planck scale, where quantum weirdness reigns supreme, spacetime itself might have resembled a boiling pot of water, bubbling with microscopic universes flickering in and out of existence. This is the realm of quantum gravity bubbles, ephemeral pockets where the fabric of reality temporarily warped, tweaking the fundamental constants that govern nuclear reactions. In these fleeting regions, the strong nuclear force could have weakened slightly, or the proton-to-neutron ratio might have tipped unexpectedly, creating bizarre chemical anomalies that still linger in the cosmos today. Imagine a cosmic lottery where every Planck-length volume of space 100 billion times smaller than an atom briefly became its own universe with slightly different physics. Most of these bubbles would have vanished instantly, but a few might have endured just long enough to skew the early universe's chemistry. Simulations from the Perimeter Institute show how even a 1 in a billion fluctuation could have left observable traces. In bubbles where the strong force weakened by a fraction, deuterium formation would have been suppressed, while zones with stronger binding might have overcooked helium into heavier elements. The smoking gun, ancient stars with bizarre isotopic ratios that defy conventional models. Take the 13 billion-year-old star SMSS 031367. It's mysteriously rich in heavy elements like strontium but poor in lithium, a pattern some theorists argue aligns perfectly with quantum gravity bubble predictions. These stars might have formed from gas clouds that passed through, or even originated within, one of these transient physics-altering zones, inheriting their strange chemistry like cosmic birthmarks. What's truly mind-bending is how we might prove this. Future gravitational wave detectors could hunt for echoes of these bubbles in the cosmic microwave background's polarization patterns. If spacetime foam was churning during nucleosynthesis, it would have left faint helical imprint spiral signatures in the oldest light we can observe. The upcoming LIGHT-BIRD satellite, set to launch in 2028, will scan for exactly these twisted polarization swirls with unprecedented sensitivity. Yet the boldest idea comes from quantum loop gravity pioneer Carlo Rovelli. He suggests these bubbles weren't random, they were quantum computations. In his framework, each bubble represented a temporary universe processor, running slightly different physical algorithms with the most stable configurations surviving to shape our reality. If true, the elements we're made of aren't just relics of nuclear reactions, they're the output of the universe's first quantum computer. It's bits frozen into atomic structures we're only now learning to decode. Deep in the subatomic shadows, there might lurk a ghostly architect of the universe's missing lithium sterile neutrinos. Unlike their ordinary cousins, these hypothetical particles refuse to play by the rules of the standard model, interacting only through gravity and possibly their own secret forces. But their greatest trick, in the early universe's searing plasma, sterile neutrinos could have triggered resonant oscillations, vanishing ordinary lithium as if it were cosmic sleight of hand. The mechanics are fiendishly elegant. Picture a dense sea of neutrinos, both the familiar types and their sterile counterparts, swimming through the primordial soup. As temperatures dropped, conditions might have briefly aligned for a phenomenon called MSW resonance, named for the Mikhail-Smirnov-Wolfenstein effect. Think of it like tuning a radio to just the right frequency. At specific energy thresholds, ordinary neutrinos would have flipped into sterile states with eerie efficiency. These conversions wouldn't just disappear particles, they'd release bursts of energy capable of shredding fragile lithium, 7 nuclei like tissue paper in a hurricane. Now here's where it gets spine-tingling. In 2022, the Mini-BUANI experiment at Fermilab detected an anomaly that sent shockwaves through particle physics. Their detector, designed to study neutrino oscillations, recorded excess electron-like signals that defied expectations. While critics argue these could stem from unaccounted background noise, proponents see a glimmer of sterile neutrinos particles massive enough to have influenced primordial nucleosynthesis. The timing fits. Sterile neutrinos in the right mass range could have triggered resonant lithium destruction precisely during the universe's first 3 minutes, leaving behind the scarcity we observe today. Ancient starlight holds tantalizing clues. The metal-poor star He-1327, estimated to be over 13 billion years old, shows lithium levels a staggering 30 times lower than Big Bang predictions. Standard models struggle to explain this, but sterile neutrino oscillations offer a clean solution. Simulations from the University of Tokyo reveal how resonant conversions would have selectively targeted lithium-7, leaving hydrogen and helium untouched, a surgical strike matching the cosmic crime scene. Yet the plot refuses to simplify. Some theorists argue sterile neutrinos could have also altered helium-3 production, while others suggest their decays might have left faint imprints in the cosmic microwave background. Future experiments like the Deep Underground Neutrino experiment aim to settle the debate, hunting for sterile neutrinos with sensitivity 100 times greater than Mini-BUANI. If they succeed, it won't just solve the lithium problem, it'll unveil a hidden player in the universe's opening act, one that danced through the primordial plasma, subtly erasing its tracks in the oldest atoms of all. The early universe wasn't just hot, it might have hit a temperature so extreme that the very rules of nuclear physics twisted into something unrecognizable. This is the daring premise of the Hagedorn temperature phase, a theoretical threshold where quark-gluon plasma didn't just behave differently, it became something entirely new. Picture a pressure cooker pushed beyond its limits. At around 2 trillion degrees, the frenzied collisions between quarks and gluons would have reached a state where conventional particles couldn't form anymore. Instead, matter would have dissolved into an anarchic soup where protons and neutrons lost all meaning, and the concept of individual elements ceased to exist. This bizarre transformation traces back to Rolf Hagedorn's revolutionary work in the 1960s. While studying high-energy particle collisions, the CERN physicist noticed something peculiar. The number of possible particle states didn't just increase with temperature, it exploded exponentially. Beyond a certain point, dubbed the Hagedorn temperature, the energy needed to create new particles would theoretically become infinite. In the first microseconds after the Big Bang, this could have triggered a phase transition stranger than anything in today's universe, a realm where matter didn't form discrete particles but fractal-like chains of energy with no fixed mass. The implications for nucleosynthesis are staggering. Under normal conditions, quarks snap together like magnets to form protons and neutrons, but during the Hagedorn phase, that binding mechanism would have broken down entirely. Instead of orderly fusion, the early universe might have experienced something closer to alchemy: random clusters of quarks flickering in and out of existence, some combining in ways that later birthed exotic isotopes we've never seen. Recent lattice QCD simulations at Brookhaven National Lab support this. When virtual quark-gluon plasmas were heated beyond Hagedorn's limit in supercomputers, they produced fleeting quark nuggets, strange, unstable conglomerates that could have skewed the primordial element mix. Here's where it gets truly wild. If pockets of the universe cooled unevenly through this phase, they might have frozen in these abnormalities. Some regions could have emerged with excess strange quarks, hypothetical particles that normally decay instantly, lingering just long enough to fuse into ultra-heavy hydrogen or helium variants. Others might have ended up with holes in conventional element production, explaining why certain isotopes like lithium-9, a heavier, unstable cousin of lithium-7, appear absent when theory suggests they should exist. The James Webb Space Telescope's observations of ancient gas clouds could hold clues. Anomalous absorption lines that don't match any known elements might be echoes of these long-vanished quark configurations. Yet the most tantalizing possibility lies in the relics. If quark nuggets formed during the Hagedorn phase, some could have survived lurking in interstellar space as microscopic dark matter candidates. The infamous "oh my god" particle, an ultra-high-energy cosmic ray detected in 1991, might have been a shard from this era, a bullet fired from the universe's most extreme furnace. Future experiments like the Large Hadron Collider's quark-gluon plasma research could recreate fleeting glimpses of this phase, probing whether nature truly allows physics to rewrite itself at temperatures beyond imagination. What makes this theory so electrifying is its sheer audacity. It suggests the elements we know are just one possible outcome, that under slightly different conditions, the universe might have forged an entirely alien periodic table. And if Hagedorn was right, then buried in the deepest layers of cosmic history lies a forgotten chapter where matter itself forgot the rules, playing out quantum possibilities we're only beginning to dream of. What if the elements we're made of aren't just products of physics, but artifacts of code? The simulation hypothesis, famously championed by philosopher Nick Bostrom, suggests our universe might be an advanced civilization's digital construct. And if that's true, the ratios of hydrogen, helium, and lithium could be more than cosmic accidents. They might be fingerprints of the simulation's underlying architecture. Bostrom's trilemma lays out the unsettling math. Either intelligent civilizations never reach technological maturity, they choose not to run ancestor simulations, or we're almost certainly living in one. But here's where nucleosynthesis gets provocative. In a simulated reality, the universe's first chemical reactions wouldn't be dictated by fundamental constants alone. They'd be constrained by computational limits. Think of it like a video game rendering only what's necessary to maintain consistency for its players. The precision of helium-4's observed abundance, matching theoretical predictions to 4 decimal places, could reflect not perfect physics but optimized rounding in the simulation's code. Astoundingly, anomalies in lithium-7's scarcity might support this. In 2022, MIT researchers ran simulations of simplified universes with reduced computational precision. Their models showed that when rounding errors accumulated during nucleosynthesis, lithium was disproportionately affected, its fragile nuclei vanishing from the ledger exactly as we observe. Even more telling, these digital universes consistently produced hydrogen and helium ratios indistinguishable from ours, as if the simulation prioritized conserving resources for dominant elements while cutting corners on rare isotopes. The James Webb Space Telescope might be unwittingly hunting for these glitches. When it analyzes the spectra of primordial gas clouds, unexplained deviations in element ratios, especially clustered in specific regions, could hint at zoning in the simulation's memory allocation. Some theorists speculate that if our universe is running on some vast cosmic GPU, lithium deserts might correspond to sectors where processing power was throttled to handle more complex calculations elsewhere. But the most haunting clue lies in quantum mechanics. The observer effect, where particles behave differently when measured, has long been debated. In a simulation framework, this could be an optimization strategy, rendering quantum states only when observed to save resources. The early universe's element abundances, then, wouldn't just be physics, they'd be a cosmic TXT file, documenting the simulation's rendering priorities during its most resource-intensive boot-up sequence. Whether you find this idea exhilarating or unsettling, it forces a profound question. If the elements are lines of code, what does that make us? The answer might be written in the oldest atoms of all, if we learn how to read between the quarks. From the violent alchemy of primordial black holes to the delicate fingerprints of quantum spacetime foam, we've journeyed through 30 breathtaking theories about the universe's first light elements. Each idea, whether grounded in ironclad mathematics or hovering at the edge of scientific imagination, reveals how much we still have to learn about creation's opening act. The stubborn lithium-7 deficit alone has spawned countless hypotheses, from sterile neutrino conspiracies to dark matter's shadowy interventions, proving that even our most refined cosmic models remain works in progress. What makes these mysteries so thrilling isn't just their complexity, it's how they connect. The same anomalies that keep physicists debating could be threads leading to deeper truths about dark matter, quantum gravity, or even realities beyond our own. When ancient stars whisper chemical secrets that defy expectations, they're not just presenting puzzles, they're offering invitations. Invitations to question assumptions, to test wild ideas, and to remember that the universe has always been stranger than we presume. So, which theory resonates with you? Do you find elegance in supersymmetry's hidden particles, or does the holographic universe's cosmic code speak to your imagination? Maybe you're captivated by rogue ideas like the simulation hypothesis or the quantum gravity bubbles that rewrite physics itself. Drop your favorite in the comments. We geek out over these cosmic debates as much as you do. And if you're hungry for more deep dives into the universe's greatest mysteries, hit subscribe. From the birth of black holes to the fate of spacetime, we're just getting started on unraveling existence's grandest stories. After all, every answer uncovered only reveals new questions, and that's what makes science the greatest adventure